All right, 7.3. Here we go. In one shot. Okay, 7.3. Simplifying and combining radical expressions. Okay, so what we're going to be doing here is we're going to take a look at multiplying, dividing, adding, and subtracting radical expressions. Okay, so we're going to go ahead and start off with the product rule. Okay, so this states that if nth root of a and nth root of b are real numbers, then the nth root of a times b is the equivalent of doing the nth root of a times the nth root of b. Okay, so you can go both directions. So if you have it already multiplied out, you can split it up. If you have it split up, you can multiply them together. Okay, so you have to take a look at the problem and see which one is more beneficial, to have it work multiplied out or to have it split. Okay, but what this is essentially saying is that if you have this, the cube root of 3 times 7, you can also split it up. Okay? And this is also saying if you have them split up, you can actually multiply them and work with just a single radical. Okay, simplified form. Simplified form of radicals. Okay, so we have all exponents of factors less than the radical index. Okay, so all exponents of factors are less than radical index. Okay, so the radical index, if you have a square root, the radical index is 2. If you have cube root, radical index is 3. If you have the fourth root, radical index is 4. Okay, so the exponents have to be less than the radical index, okay, in order to be simplified. Also, no fractions or negatives inside radical. Okay. If you do have fractions, then you have to split it and rationalize the denominator. Okay. And no radicals in the denominator. That kind of goes with fractions. Okay, so same thing here. If you have a fraction in the radical, or if you have a radical in the fraction in the denominator, then here in both situations, we'll have to do what's called rationalizing the denominator. Okay, so let's take a look at simplifying using that product rule. Okay, so simplify. Okay, so let's take a look at this first example, square root of 12. Okay, so clearly 12 is not a perfect square. So you might look at this and think, oh, there's nothing we can do. But because we have the product rule, it says, well, you can split it up. And you might be thinking, well, why would I want to do that? And how would I do that? Okay, so we're going to go ahead and use the product rule, and we're going to split the 12. Okay, so our choices are 2 times 6, 3 times 4. Okay? That's how you can split up 12, right? Which choice do you go with? You go with the choice that has a perfect square since you're dealing with a square root. Okay? So what you want to do is you want to split this 12 up using two numbers where at least one of them is a perfect square. So you don't want to go with 2 and 6 because 2 and 6 are not perfect squares. So we want to go with 4 and 3 because 4 is a perfect square. So we can simplify this one. Okay. So you're simplifying if you can at least simplify one of them. And that would be our answer. The one that doesn't simplify, square root 3, just comes down. Okay. And this would be your simplified answer. Okay. Let's try another one. Let's take a look at square root 98. Okay. Again, 98 is not a perfect square, but we could split this up. Okay. So we could split this up using two numbers where one of them is a perfect square. Okay. So can anybody think of a perfect square that we can break this up with? 49 times 2, right? 49 times 2. Okay. And here we can simplify the square root of 49, which is 7. And then the square root 2 comes down. Okay. All right. Let's take a look at this next example. 5. And now we're dealing with the cube root of 54. Okay. It might help to write down like your perfect squares and then another list of your perfect cubes so that you can look at your perfect cubes to see which one of those will work. Okay, so here I'm going to keep that 5 that's on the outside, but I want to break up the 54 using a perfect cube. So if you don't know your perfect cubes, then I would recommend listing them. So I can see here that it would be 27 times 2, where 27 is the perfect cube. All right, so cube root of 27 is 3. And then this cube root of 2 won't simplify, so that would remain. And then here I can multiply the 5 and the 3. And the cube root of 2 remains. Okay? And let's take a look at this next one. Negative fourth root. Let's do fourth root of 48. Okay? So same thing. If you're not familiar with your powers of 4, let's start. 1 to the 4th is 1. 2 times 2 is 4 times 2 is 8 times 2 is 16. Okay. 3 times 3 is 9 times 3 is 27 times 3 is 81. So we've already gone beyond it. But we can see here, okay, so this is 1 to the 4th. This is 2 to the 4th. This is 3 to the 4th. And we can keep going. But we see here that 48 is divisible by 16. So that's what I'm going to use. So this negative 1 will stay out here. And I'm going to break up the 48 using 16 times 3. Okay, so that's negative 1 times the fourth root of 16 is 2. And this one doesn't simplify, so I'll bring it down. So this is going to be negative 2, fourth root of 3. Okay. Very good. All right. Let's take a look at some that have variables in it. These all were just numbers. So let's take a look at examples with variables. Okay, so here, m to the 9th. Okay, So many different ways to do this. So if you don't quite understand the method I'm doing here, feel free to go on YouTube and search uh, simplifying radicals with variables. Okay, so I'm going to use the idea that radicals roots can be rewritten using fraction exponents. Okay, so I'm going to go ahead and rewrite this as 9 over 2, right? Because square root is 1/2, right? And then I'm going to simplify that fraction. 9 divided by 2, I'm going to turn it into a mixed number. So I'm going to do 9 divided by 2, which is 4, and I have a remainder of 1. So that's 4.5, right? I forgot my m. Okay, so all I did was turn this fraction into a mixed number. Just do this division. 9 divided by 2 is 4, so you have a whole number 4, but then you have a remainder 1, so that goes up here, and then the denominator stays the same. Okay, so I get m to the 4.5, right? And I can split this up as m to the 4, m to the 1/2. Okay, and so here it's easy for me to see what's going to be left inside the square root. It's going to be this one. Okay, so m to the 4th will be out here, and m will be in here, m to the 1st power, because that's a 1. So this would be our final answer. Okay, let's take a look at another one. Let's have 10 outside, square root 128a5. All right, so first of all, let's take care of the number first. So that there I can use here. I'm going to bring that 10 over. I'm going to break this up. Okay. I'll do the a over 5/2. Okay. This is going to be, I'm going to use 64 times 2. Okay. So that's going to be 10. That's going to be 8. That's going to stay. And here, now I take care of this and turn this exponent into a mixed number. So that's going to be 2 goes into 5 twice with a remainder of 1 over 2. Okay. So here, 10 times 8, that's 80. Okay. And then here, I'm going to split this up. That's a squared and a to the 1/2. Okay. So I can see now what's going to go under the radical. This will be under the radical, and this will be under the radical. So 80 a squared will not be under the radical. 2 and a to the 1st will be under the radical. Okay. Okay, let's take a look at another one. Let's do cube root. Negative 24 x to the 5th. Okay, so I am going to break up the 24, and then I'll do the x as a fraction, 5 over 3. Okay, so I need a perfect cube to make 24. So that's going to be negative 8 times 3 to make negative 24. Okay, negative 8 is my perfect cube, so it's going to be negative 2. This one will stay. This here, so I'm going to turn this fraction into a mixed number, 5 divided by 3. That is 1 with a remainder of 2 over 3. Okay, now let me split this up as x to the 1st and x to the 2/3. And bring these guys over. So that's x to the 1st and x to the 2/3. So now I can see what's going to be going inside the radical. This will stay in the radical, and this will be under the radical. So negative 2 and x will be outside, and then 3 and x squared, because remember, this is an x squared, that's under the radical. Okay, hopefully that makes sense. Here, why don't we'll do one more and then I'll have you try. Here, why don't you try this one? Fifth power, a to the ninth, b to the fifth. Okay, go ahead and hit the pause button. Okay, so these here are both variables, so we're going to go ahead and rewrite them as with fraction exponents. Okay, and now let's go ahead and do that division. 5 goes into 9 once, with a remainder of 4. B, 5 goes into 5 once. Okay, so I'll split up the a to the first, a to the 4/5. So we see here only the ones with the fraction exponents will be left in the radical. So only this one will be in the radical. Okay, so you can see that here. That's clearly under the radical. Between these two, the one with the fraction. Okay, again, that's clearly under the radical. And between these here, the one that's a fraction will be in the radical. Okay, so here, this one, the fraction, will be in the radical. So a to the first, b to the first will be outside the radical, and a to the fourth will be inside. Okay? Okay, so that's the product rule. Let's take a look at the quotient rule. All right, so it states that if nth root of a and nth root of b are real numbers, then, similar to the product rule, if you have this division, it's the equivalent of splitting them up. Okay, so again, you could either, if you have a quotient, you can split them up and maybe you can simplify one of them. Or if they're already split, if they can't be simplified, then maybe put them together and you can simplify. Okay, so be able to go that way, split them up if you need to, or put them together if you need to in order to simplify. Okay, so for example, you might have something like this, right? When they're together like this, you can't really split them up. I mean, you can't really simplify them. So if you split them up, you can simplify at least the square root 64. Square root of 64 is 8. Okay, so that's what we mean. Okay, so let's take a look. Let's go ahead and try these. We'll just do 3. Okay, so suppose that we have 15 over 49x squared. Okay, so I can't simplify these. They don't have anything in common, right? And it's not a perfect square. But if I split them up, I can see here that I can simplify the denominator. Okay, so I will keep the square root 15, but down below I get 7x. Okay. Okay. 7x or 7 absolute value x, because we are taking the square root. Okay, let's take a look at this next one, cube root. 10x squared, 27 y to the 6th. Okay, again, when they're together like this, I can't simplify them. But if I split them up, I can simplify that denominator. Okay, so I will keep this. Can't do anything there. But down here, the cube root of 27 is 3. And over here, what's being cubed? Y squared to make 6, right? Okay, so y squared. Okay, and let's do one more here. Cube root 25 over 27. So clearly that doesn't simplify. So if I split them up, then here this remains, and this here I get 3. Okay. All right, so we see here that when I simplified these 3, it satisfied those conditions that I listed about how you know you're simplified. So here we don't have, here we had a fraction inside the radical, and it said no fractions inside the radical. And so when I have it here, I don't have the answer here. There is no fraction under the radical. Okay, and then same thing here. There is no fraction under the radical. Only 25 is in the radical. Okay, and then it also says something about how no radicals in the denominator. See this? You have radical in the denominator. Well, our final answer, we don't have radical in the denominator, so we didn't have to worry about that. Okay, so let's take a look at the case where you do have a radical in the denominator, okay, or you have this fraction inside the radical. Okay, so rationalizing denominator. Okay, so we want no fractions. We want no fractions inside radical. And we want no radicals in denominator. Okay. Okay. If simplifying like above, like the problems that we did above, if by simplifying you don't get this result, like these worked out nicely, right? But if they don't work out nicely like that, then you're going to have to rationalize the denominator. Okay. So rationalize denominator if simplifying doesn't work. Okay, so rationalizing the denominator. So radicals, like if you have square root 5 in the denominator, then your denominator, it's a real number, but it's an irrational number. Square root 5 is an irrational number. Okay, it's a decimal number that goes on forever and ever without repeating. Okay, whereas if you just had 5 in the denominator, 5 is a rational number. Okay, so but square root 5 is not. So when we say we're going to rationalize the denominator, what you're doing is you're going to take the denominator and you're going to rationalize it. You're going to turn it into a rational number. Okay? All right, so let's take a look. Okay, so if I have this, we'll start off simple. Square root of 2 over 3. Okay, so I can't simplify this. And if I split them up, I still can't simplify this, right? There are 2 is not a perfect square, 3 is not a perfect square. So I need to rationalize the denominator. Okay, so what I have to do here is turn that square root 3 into a rational number. And the way you do that is by multiplying. Since this is a square root, I can just multiply by square root 3 over itself. Square root 3 over square root 3. Okay, and what happens is when I do this, right, I'm really only multiplying by the number 1 written in the form of square root 3 over square root 3, right? Okay, so I'm not changing the value of this. Okay, so what happens is now, instead of having square root 3 in the denominator, I'm going to have square root 9, which simplifies to 3, which is a rational number. Okay, so that's how we take care of it. All right, so up here, I get square root 6. And then down below here, I get square root 9, but then that simplifies to 3. And now I don't have that radical in the denominator. Okay? All right, let's take a look at another example. Let's take a look at this one. Simplify. Suppose that I have a 45xy squared over square root 5x. Okay, so don't jump the gun and start rationalizing. Check to see if you can simplify it first. So here, let's go ahead and see what happens if we rewrite this as a single radical, 45xy squared over 5x. Oh, well, if I do that, well, then 5 here will cancel. And this, what is that? Is that an x? Yeah. And then this x cancels, right? So now I'm left with square root of 9y squared. Okay, and I can simplify this further, but at least I've taken care of the radical or the fraction that's in the radical, and I can just take care of this, which is 3y, and this simplified without me having to rationalize the denominator. Okay. All right, let's go ahead and take a look at this one. Suppose that you have to simplify square root 3 over square root x. Okay, so here, even if you write this as a single radical 3 over x, it's not going to simplify, right? So, so this is one of the cases where you would have to rationalize that denominator. Rationalize that denominator. Okay, so here, let me bring it down here. Square root 3 over square root x. And so here we are going to go ahead and multiply it by square root x over square root x, which is 1, right? That way down below, I get square root of x squared, which will simplify, okay? So here in the numerator, I get square root 3x, but down here, I get x squared, but the square root of x squared is just x. Okay. All right, so that's how you take care of your denominators if you have radicals in your denominators. Okay, let's take a look at adding and subtracting. Okay, so when you add and subtract radicals, they need to be like terms. And so they are like terms if they have the same radical. So like square root and square root. You can't add square root and a cube root, okay? So they have to have the same radical. And radicand. Fancy word. Okay, so that's the thing that's inside the radical. Okay, so for example, these three terms, 2 cube root 3 of 5, negative 4 cube root 3 of 5, and 9 cube root 3 of 5. All of these are like terms, okay, because all of these are cube roots, and all of these are cube roots of 5. Cube root of 5, cube root of 5, cube root 5, okay? So here's an example of not like terms. So if you have like square root 5 and you have cube root 5, okay, not like terms, okay? So they have to be the same radical, okay? So they have to both be square roots, like square root 5, or they have to be cube root 5, cube root 5, okay? All right, so let's go ahead and simplify these. All right, let's do this first one. 18 plus 2 cube root 3 plus cube root 3. Okay, so we have three terms here, but only two of them are like terms. These two are like terms. If you don't see a number out here, it's 1. Okay, and so we have 2 plus 1. So we get 3 square root 3's. And you just bring down that 18. Okay. Suppose we have this 18 plus 2 square root 12 minus 3 square root 48 plus 9. Okay, so we have 4 terms, 1, 2, 3, 4. You might be looking at this thinking, okay, well, 18 and 9 are the only things that are like terms. Okay, and at first glance, it might look like that is true. But if you look a little closer, this here can be simplified, and same thing with this square root 12. Okay, so let's go off to the side. Okay, so let's go ahead and simplify those. 2 square root 12. I'm going to go ahead and break up the 12. Okay, so I'm going to break up the 12 using 4 and 3. So then that gives me 2. Square root 4 is 2, and then the square root 3 stays. So this is going to be 4 square root 3. Okay, so let me rewrite the 2 square root 12 as 4 square root 3. Okay, let's do the 3 square root 48. Okay, so here I'm going to break up the 48 using two numbers. I'll use 16 and 3. 3 times 16 is 48, right? Yeah. Okay, so square root of 16 is 4, and the square root 3 stays. So this is really 12 square root 3. So I'm going to replace that with 12 square root 3. So now we see that these are actually like terms. Okay, so 18 and 9 can be combined, and 4 square root 3 minus 12 square root 3 can be combined. Okay, so we get 18 plus 9 is 27, and then positive 4 and negative 12 is negative 8 square root 3's. Okay. All right. Why don't you go ahead and try this one? And we'll end here. I think we're going to end here. Yes. Okay, so make this a good one. Try this out. See if you can get it. Simplify your radicals first if possible, and then check to see if you have like terms. Okay, go ahead and hit the pause button. All right. Okay, I'm just going to do the work here instead of off to the side. Okay, so I need cube root and 16, so I'll use 8 and 2. Here, 54 cube roots, so perfect cube, I'll use 27. 27 times 2. And then here, I'll use 8 times 3. All right, so let me simplify these. Cube root of 8 is 2. Cube root of 27 is 3. Cube root of 8 is 2. Okay. All right, so here we see that these two are actually like terms. This one is not. So here I can go ahead and combine, and I get 5 cube root 2, and then I'll bring this one down. Okay. All right, so that is it. If you have any questions, or if you want another video or something that goes a little bit deeper with the simplifying the radicals with the variables, or any topic, you can say, oh, is there not, you can just text me, email me, and say, oh, is there another video that explains this part a little bit more? And I can find one that I think is sufficient, or you can just YouTube it yourself. Okay. Email me or text me if you have any questions.